Alright, so in this video, what I'm going to have you do is, once I get you set up, pause the video and then see which answer choice you would pick. Okay? So this one, are you going to pick A, B, C, or D for the correct free body diagram? Okay? And it's from this statement. An object is pushed at a constant force, so that means this is not changing, and it also says it's moving at a constant speed. So, pause the video, see which free body diagram you think is correct. Alright, so now you've submitted your answer there. Let's look through these and see what happens. So, the first force. We always know gravity's there. These are all assumed to be on Earth, and gravity is going down or to the center of the planet. So we have all of those. Next, normal force needs to be perpendicular to the surface. I can see all of these have a normal force perpendicular to the surface, and they also have a frictional force that is parallel to the surface. So just my definitions work, and then I can see they all have the correct angle. Again, the angle here is from the horizontal. The angle here, it's written a little differently, is from the horizontal. When we're drawing free body diagrams, all of our forces originate at the center. So that's what we're looking at here. So now let's look at our x and y components, because whenever we're doing this, you need to break it up into x and y. So if I pull down and to the left, I pull to the left and down. That looks pretty good. I pull to the left and down. Again, tip to tail. Here I pull to the left and down. That looks good. Here I pull to the left. Whoops. This has pulling up. So this cannot be an answer choice. The next one, let's look at, we've done our definitions, we've done components. Now let's see what works for Newton's, not second law, Newton's first law, Newton's second law, and also Newton's third law. Well, Newton's third law are on opposite objects. I only have one free body diagram, so that's not going to be it. So let's look at Newton's first law. Here it's constant speed, so the forces must be balanced. So let's look in our x direction. Here I can see, based off of my grids here, okay, that it starts at the half point. So there's a half, there's one, there's another, there's two. So I have 2.5, there's 3. So I have 3 vector forces to the left, so I need 3 to the right. That is not 3 to the right, so that can't be an answer choice. This one, right? Again, I have, there's 3 to the left, and I have, there's 2 plus that, there's 3. So that looks good. Down here, okay, that's the exact same, so I'm getting closer. Then let's do Newton's first law up and down. It is also not accelerating up and down, so they should be the same. So how many do I have going down? There's 1.5 and 1.5. So if I have total of 3 going down, I need a total of 3 going up. And that's what I have right here, so that looks good. Here I have 1.5 down, 1.5 down, so I have 3 down. I must have 3 up. Oh, I don't have 3 up, I only have 1.5 up. So this one cannot be the answer. So our answer choice, hopefully you picked, was B. All right, let's go to the next one. All right, so here, what I want you guys to do, pause the video, try and answer the questions. You'll then be prompted to put in your answer choice. Again, your answer choices, if it was free response, they would be like this, and it say you can only have f m cosine theta. So again, it's the same exact prompt, constant force, constant speed, but now solving for the force of friction. Right, remember, be a kitten, free body diagram, net force statement. That's how you solve all forces problems. So give it a shot, see what you get. All right, so let's look at it. I have my free body diagram, which we could see back here. Okay. Then let's break this down into net force in the x equals max, and net force in the y equals may. If I look at these two choices, force of friction is in the x, so that's probably how I'm going to solve this one. Force normal is in the y, so that's how I'm going to solve this one. So arrows to the right. Let's make right positive. So here I have force of friction minus force in the x, then must equal max. Well, it's at constant speed, so my acceleration is 0, so this whole side is 0. So the force of friction equals that force in the x direction. I look here, that force isn't there because I have force in the x, and that's not a variable. So that means I must do trig to solve that force in the x. If I look here, I can see that this is the adjacent to that 30-degree angle. So that means I must use cosine. So this is F cosine theta for that force of friction. From there, let's see what the next one is. So, F net and the y. What arrows are going up? I can see those in the blue, highlighted right here. So here I have Fn going up, minus Fy going down, minus force of gravity equals, again, it's not accelerating, so that's 0. So force normal must equal force y plus mg. So I can go down here. Hey, there's only one that has plus mg, so it has to be that one. And that trig function would prove. So we said this one is A, and this one should be C. All right, let's go to the next one. What would happen if the angle decreased? So instead of pushing here, what would happen if I then pushed at a lower angle? All right. So as we're back to this one, seeing what would happen to that angle. So you can look at it multiple ways. You could go back and see your equation for Fn is this one right here. So when I lower that angle, am I changing mg? No. But what's happening when I do F sine theta? And you could play with some and see what happens mathematically. Essentially what would happen is your your F sine theta is going to be less because you're getting less in the y component. So if I do that angle going down that way, that's going to get less than my Fn should get larger. Now I believe, let's see, that we're good there. So that should get smaller Fn if I push at a different angle. Okay. But let's see conceptually, just does that make sense? Well, so what we started with here, let's erase that, is this has a y component pushing down. And I have gravity pushing down. So both of these pieces are pushing down. And then the normal force has to push back to cancel out. So as you can see, when I had that green one in there, right, I don't push down as hard. So I'm not pushing down as hard, so the normal force doesn't have to work as hard, and it can push back less. So again, that would lead me to a decrease that we could see right there. All right, now it's changing. Our prompt is changing. We're going to push at a constant force, and it accelerates. And here now it wants our answers in terms of these variables: force, force of friction, mass, and theta, and then any fundamental constant, which is typically g or any other constants. All right, so let's set up. Again, free body diagram. Okay, it's our same free body diagram. We're just pushing the opposite way. So I have this force here. Better break that force into force in the x, force in the y. Gravity's still there. Normal force is still there. And now we have the force of friction. Now again, it accelerates. So force in the x must be greater than force of friction. So if we're looking for acceleration, that is in the x direction. So I'm going to start here. F net in the x equals max. So here I have force of x minus the force of friction equals max. So to solve for acceleration, I would just divide by mass, divide by mass. So there's my equation for my acceleration. The problem is, that's not in my answer. Well, I have to have these variables. So I had to go a step farther and break down f of x using trig. From this angle, that f of x is the adjacent piece, so it must be cosine theta. But again, as you can see, it definitely is force in the x minus force of friction. There's only one answer with that, so it must be C. All right, let's look a step farther. Okay. So here we have which statement best explains the situation. If you notice, I have best underlined. So again, pause it, see what you can do. You'll be prompted to try and solve this, and then let's see. So breaking this down to solve, we would break this into t2 in the x, and then t2 in the y. I also have gravity, don't forget about that. And so now we want to start comparing. So if we look here, these are asking about T2 and they're asking about mg. Is this in the x or in the y direction? It's mg that's in the y direction. So I'm going to start with F net in the y equals may. These are at rest, so that's 0. So here I have T2 in the y minus mg equals 0. So T2 in the y must equal mg. So then just understanding trig, T2 in the y is a component where T2 is a hypotenuse. A hypotenuse is always bigger than a component. So that tells me T2 must be bigger than mg. So that looks good. But I got a problem. This is also bigger than mg, but it gives me a specific value. Is it double mg? Right. So if I needed to look at this a little bit more, right, now I can do my trig. Right. So I know this component is equal to mg because T2y equals mg, and this is 30 degrees. And then we're trying to solve for T2. Right. Well, I know that the sine of 30 is 1/2. What does that mean? That means the opposite over the hypotenuse is at a 2-to-1 ratio. Oh, that's double. Another reason I like to think about this, that means that the opposite is half the size of the hypotenuse, or you could say the opposite is 50% of the hypotenuse. So there's all kinds of different ways to understand what that is. But that ends up, this is a better value because it is exactly 2 mg rather than just mg. So the next scenario goes in comparing T1. And so then if we're looking at T1, that's in the x direction. So F net in the x equals max. Again, it's at rest, so that's 0. So here in the x direction, I have T1 minus T2x equals 0. So T1 must equal T2 in the x direction. So this is a component, a side of a triangle, and this is the entire thing. So T2 is the hypotenuse, and the hypotenuse always has to be bigger than a component. So T2 must be greater than T1. So it can't be this one, and it can't be this one. But both of these have T2 being greater than, T1, there it is. Right. So then I have to compare mg and T2. Right. Here, this is just a little bit of, again, some trig analysis. So again, we have our sides of our triangle. So we know this is mg. And then I can see T1 must equal T2x. So this side is equal to T1. This is 30 degrees. And I know at 45 degrees, so if it was a little bit higher, 45 degrees, x equals y component. But if I lower it, then I know that the x component is greater than the y component. Right? So that means T1 must be greater than mg. So if we look at that, that gives us answer choice D. So those are some great challenging problems that would prepare you for the level of questioning on the AP test.